This is Britain, or rather, this is the coastline of Britain, drawn from publicly available cartographic data. How long is it? That question has no single answer. The CIA World Factbook says 12,429 kilometers. The British Cartographic Society lists 17,820. Encyclopedia Britannica gives a different number again. Same coast, same day. The disagreement is not about measurement error. It is about something deeper. If you walk along the coast with a 200-kilometer ruler, planting one end every 200 kilometers and counting the steps, you get about 2,200 kilometers in total. Now do it again, same coast, but use a 50-kilometer ruler. The total comes to 3,300 kilometers, 50% longer. The smaller ruler is not more accurate. The bigger ruler is not lazy. Both are measuring exactly what they were told to measure. They simply produce different numbers because the question, surprisingly, depends on the ruler. Here is what is happening. Zoom into a single section of the coast. When the 200-kilometer ruler walks past, it cuts a straight line across this bay. It does not enter. From the ruler's point of view, the bay does not exist. Replace it with a 100-kilometer ruler. Now the new ruler can enter the bay. It hugs the curve. It adds 30 kilometers of coastline that the bigger ruler simply walked past. Shrink the ruler again to 50 kilometers. The ruler now finds smaller coves inside the bay. Another 40 kilometers appears, 25-kilometer ruler. Sea stacks, inlets. Each new resolution reveals coast that the previous resolution missed. If you tabulate this honestly, the pattern is unmistakable. 200-kilometer ruler, 2,200 kilometers. 100, 2,800, 50, 3,300. 25, nearly 4,000. The total length does not converge. It keeps growing. Plot the data points on logarithmic axes. They fall on a straight line. The growth is not random. It follows a precise mathematical law. The reason the length keeps growing is that Britain's coast has detail at every scale. Take any small section. Zoom in. New wiggles appear. Zoom into one of those wiggles. More wiggles. Each level of magnification reveals structure that was invisible at the previous level. This is not a coincidence of one coast. It is a property mathematicians call self-similarity. The classic illustration is the Koch snowflake. Start with a triangle. Replace each edge with 4 smaller edges. Repeat forever. At every magnification, the snowflake looks structurally identical to its parent. Put Britain's coast next to the Koch snowflake. Zoom into both at the same rate. They behave identically. The coastline is, in a precise statistical sense, a fractal, a shape whose detail does not end as you zoom in. This is why the length depends on the ruler. The bigger the ruler, the more detail it ignores. The smaller the ruler, the more detail it captures, and there is no smallest scale. Benoit Mandelbrot, in 1967, made this idea quantitative. He observed that for fractal coasts, the total length L and the ruler size S are related by a power law. L is proportional to S raised to the power 1 minus d. The exponent d is called the fractal dimension. For a perfectly smooth curve, a circle, a straight line, d equals 1. The length is constant, no matter what ruler you use. For a shape so wiggly that it fills space, like a piano curve, d equals 2. The length is infinite at any non-zero ruler size. Real coasts sit in between. Britain measures d approximately equal to 1.25. Australia is 1.13. South Africa, with its smooth Cape Coast, is 1.02. Norway, with its deep fjords, is 1.52. The fractal dimension is a number that measures roughness. The higher the dimension, the more coast is hidden between any 2 points. And here is the consequence. For any coast with dimension above 1, shrinking the ruler sends the total length to infinity. Britain's coast, measured at infinite precision, has no finite length. The length is unbounded. The coast, in a strict mathematical sense, is not measurable. This is not a quirk of cartography. It is a fundamental property of nature. Lightning has a fractal dimension of about 1.1. River networks between 1.1 and 1.3, the branching of human lung alveoli, 2.97, almost completely filling the chest cavity. The surface of broccoli florets, around 2.66. These shapes were here before mathematics noticed them. Calculus, the foundational tool of physics, was developed in the 17th century on the assumption that nature is smooth, that curves have well-defined lengths, that surfaces have well-defined areas. Mandelbrot's central insight was that the smooth case is the exception. Most of the natural world, lightning, coastlines, lungs, snowflakes, mountain ranges, blood vessels, is fractal. The calculus we built does not apply to it directly. Whole new branches of mathematics have grown up to handle these objects: fractal geometry, scaling theory, the analysis of self-similar processes. So the next time a map labels a coastline with a number, remember what that number means. It is the length the coast appears to have when measured with a particular ruler. Use a different ruler, get a different number. There is no true value. The coast of Britain does not have a length. It never did.